Suppose you want to take 6 courses, but some courses must be completed before others. The college website needs to place all 6 courses in an order that follows those prerequisites. An arrow from Intro to Programming to Data Structures means that Intro to Programming must come first. Every arrow in the graph represents the same rule. Here is one order that works: Intro to Programming, Discrete Math, Linear Algebra, Data Structures, Algorithms, and Artificial Intelligence. Every prerequisite appears before the course that needs it. We could also put Linear Algebra before Discrete Math. That still works because these two courses do not depend on each other. So the same graph can have more than one valid order. Now suppose Artificial Intelligence is also a prerequisite for Data Structures. Would that work? Nah, you could not take Data Structures until Artificial Intelligence was completed. But Artificial Intelligence needs algorithms, and algorithms needs data structures. Each course is waiting for another course in the same loop, so none of them can go first. This loop is called a cycle. Real course plans should not have a loop like this. Remove that extra arrow, and the graph still has directions, but it has no cycle. That makes it a directed acyclic graph, or DAG. An order that follows every arrow is called a topological order, and finding that order is called topological sorting. So how does the website find one? Start by writing 0 next to every course. Then go through the arrows one by one. Whenever an arrow points into a course, add 1 to that course's number. The first arrow points into Data Structures, so its number changes from 0 to 1. Data Structures points into Algorithms, so Algorithms also changes to 1. Discrete Math adds 1 more to Algorithms, so Algorithms becomes 2. Algorithms adds 1 to Artificial Intelligence, and Linear Algebra adds another, so Artificial Intelligence also becomes 2. This number tells us how many prerequisites a course is still waiting for. The standard name for it is in degree. Which courses can we take immediately? Intro to Programming, Discrete Math, and Linear Algebra have an in degree of 0. They are not waiting for anything, so we put them into a queue. When one course is completed, only the courses directly after it can change. So beside every course, we also store the courses that it unlocks. This is called an adjacency list. The queue begins with Intro to Programming, Discrete Math, and Linear Algebra. We remove the course at the front and add it to the final order. Intro to Programming leaves first. It unlocks Data Structures, so the in degree of Data Structures drops from 1 to 0. Data Structures is now ready, so it joins the queue. Discrete Math leaves next and lowers the in degree of Algorithms from 2 to 1. Algorithms still has 1 unfinished prerequisite, so it cannot enter the queue yet. Linear Algebra lowers Artificial Intelligence from 2 to 1. Artificial Intelligence is also still waiting for 1 course, so it remains outside the queue. Data Structures now leaves the queue. This removes the last unfinished prerequisite from Algorithms, so Algorithms reaches 0 and joins the queue. Algorithms leaves next and lowers Artificial Intelligence from 1 to 0. Artificial Intelligence joins the queue, then leaves last. The queue is now empty, and all 6 courses are in the final order. Every prerequisite appears before the course it unlocks. This process is called Kahn's algorithm. Why is it always safe to take a course with an in degree of 0? Because it is not waiting for any unfinished prerequisite. Everything it needs has already been completed. Now add the arrow from Artificial Intelligence back to Data Structures. Intro to Programming, Discrete Math, and Linear Algebra can still be completed, so the algorithm begins normally. After those 3 courses are completed, the queue becomes empty. But Data Structures, Algorithms, and Artificial Intelligence are still unfinished, and each one still has an in degree of 1. Data Structures is waiting for Artificial Intelligence. Artificial Intelligence is waiting for Algorithms, and Algorithms is waiting for Data Structures. The algorithm is stuck because these courses form a cycle. This is why a graph without a cycle must always have at least 1 course with an in degree of 0. If every course was waiting for another course, following those prerequisites would eventually bring us back to a course we had already visited. That would create a cycle. So the cycle check is simple. If the final order contains every course, return it. If some courses are missing when the queue becomes empty, the graph contains a cycle. The Python program follows the same steps. We import deque from collections, then create a function that receives the list of courses and the prerequisite pairs. First, create an empty adjacency list for every course. Then, create another dictionary where the in degree of every course starts at 0. Each prerequisite pair contains 2 courses. The first course must be completed before the second. We add the second course to the first course's adjacency list, then increase the in degree of the second course. Once every prerequisite pair has been processed, collect all courses with an in degree of 0. These courses go into the deque, and the final order begins as an empty list. While the deque is not empty, remove the course at the front and add it to the final order. Then, go through the courses that it unlocks. Lower each in degree by 1, and whenever an in degree reaches 0, add that course to the deque. When the loop ends, compare the length of the final order with the total number of courses. If the lengths are different, return an error because the graph contains a cycle. Otherwise, return the completed order. Run the program with our 6 courses and 5 prerequisite pairs. The result contains all 6 courses, and every prerequisite appears before the course that needs it. Now, add artificial intelligence as a prerequisite for data structures. This time, the deque becomes empty after only 3 courses, so the program reports a cycle. Each course enters the queue once, and every prerequisite arrow is processed once, so the running time is O of V plus E. The adjacency list also uses O of V plus E space. At the beginning, 3 courses have an in degree of 0. We chose Intro to Programming first, but discrete math or linear algebra would also have worked. A queue chooses the course that entered first. A stack would choose the most recently added course. The final orders may look different, but both can still follow every prerequisite. If we need the same result every time, we can use a min heap. It still stores only the ready courses, but it always removes the alphabetically smallest course. The ready courses also tell us whether the topological order is unique. If 2 courses are ready at the same time, either one can come next, so more than one valid order exists. A topological order is unique only when exactly one course is ready at every step. Our graph begins with 3 ready courses, so its order is not unique. Kahn's algorithm builds the order from the beginning. Depth-first search takes the opposite approach and builds it from the end. Start from Intro to Programming and follow its arrows through data structures and algorithms until we reach artificial intelligence. Should Intro to Programming enter the final list immediately? Not yet. With DFS, a course is added only after every course that depends on it has been completely explored. Artificial intelligence has nowhere else to go, so it enters the finished list first. Then Algorithms enters, followed by Data Structures and Intro to Programming. Discrete math and linear algebra are added after their paths are finished. The finished list is backward, so we reverse it. After reversing, every prerequisite appears before the course that depends on it. This works because if one course points to another, DFS finishes the second course before adding the first. Reversing the list places the first course before the second, which is exactly what the arrow requires. DFS uses 3 states to find cycles. White means the course has not been visited. Gray means it is still on the current path. And black means it is completely finished. If DFS finds an arrow pointing to a gray course, it has returned to a course on the current path. That means the graph contains a directed cycle, so no topological order exists. DFS also visits every course and every arrow once, so its running time is O of V plus E. Its recursion stack can use up to O of V additional space. Course prerequisites are only one example. Build systems use the same idea when one file depends on another. Package managers use it for software dependencies, and task systems use it when one job must finish before another can begin. In every case, topological sorting gives us the same promise. If there is an arrow from one task to another, the first task will appear earlier in the order. It does not tell us the fastest schedule, how many workers we need, or how long the work will take. It only tells us which tasks must come before others. Use Kahn's algorithm when you need to see which tasks are ready, detect whether the order is unique, or process tasks as they become available. Use DFS when the program already uses graph traversal, and building the order in reverse fits naturally. Kahn's algorithm removes courses with 0 in degree. DFS adds courses after their outgoing paths are finished. Both produce a topological order, and both fail when the graph contains a directed cycle.